So there's one last idea I want to list here, which is uncertainty. So I'm not listing this as one of the 5 principles of quantum mechanics because it can be derived from other things. There's a more general definition, I think, derivation in chapter 5 of Townsend, which is, I think, a little clunky. You'll do probably a more elegant approach to this in 421. But let me just remind you, right? So we've learned about the Heisenberg uncertainty principle that says that the uncertainty in x times the uncertainty in px is greater than or equal to. Okay. So it turns out that this is actually a special case of a more general idea. Right? More generally, uncertainty and uncertainty principle turns out any two what are called non-commuting and so what two operators to commute means is that the order doesn't matter, that you can apply one first and then the other, or the other way around, and you get the same thing. That's not true for position x, p, x don't commute, right? So just to think about it, right, so if I were to apply x and then px to some wave function, right, and I'm not going to write the functional dependence, right, this says, right, that this is, the first thing I have to do is to act the momentum operator on my wave function, and then, multiply by x, so I have x times minus I h bar d psi dx, right, and that is not equal to the other way around, right? Which would be minus I h bar times the derivative of x times my wave function. Right? I think you know that, right? If you do this, right, you have to product rule the derivative here, right? So there's going to be an extra term compared to here. Right? And so it turns out there's a deeper relation between non-commuting operators and uncertainty. It has to do with the fact which you might study in linear algebra, might have seen in linear algebra, and you definitely will talk about in 421. So in the linear algebra context, for folks who may have seen it, if I have two matrices that commute, I can always find a simultaneous set of eigenvectors for those matrices. The same sort of idea carried over to operators is what underlies the more general uncertainty principle. But I just want to mention this now because that's sort of the last really important idea we've talked about, and sort of all that we've done in the last couple of weeks can really be summed up in those 5 general principles, plus thinking a little bit about uncertainty. I want to just take a couple of minutes now to talk about interpretation in quantum mechanics. We haven't spent a lot of time on this yet, but there are some really deep questions you could ask, and if you haven't asked them, but I think they're worth thinking about. So, right, we've seen that, for instance, particles don't have a definite position. That, for example, So what does it mean to not have a definite position? There are, I think, roughly speaking, sort of three possible schools of thought here. So one school of thought, right, which we might call sort of the realist position, is to say, right, the particle really does have a definite position, but we just can't know it. But right, so that's sort of one school of thought. School of thought B is what we might call, so there are what folks might call sort of the orthodox, and maybe that's too strong because it sort of suggests majority here, but we might think of this as sort of matter wave as the other way we might think about it. No, so which is more. This is more or less along the lines of what I have been saying throughout the course, that the particle really doesn't have a well-defined at least before we make a position measurement. And then there's school of thought C. Well, school of thought B, sort of then you're left with, well, measurement is weird, right? And that's kind of what we talked about already with the idea of wave function collapse. But then there's sort of the last school of thought, which in my mind is maybe the least satisfying, is sort of what I'd call an agnostic, which is that this is not so what, whether or not the particle has a definite position or not, this is not a useful question. Sort of avoid thinking about questions of interpretation, and perhaps the best way to summarize this would be a quote perhaps apocryphally attributed to Richard Feynman, namely, "Shut up and calculate." Now, I have to say that I do not fall into this agnostic camp here. I think these are really interesting and worthwhile questions to ask, and I certainly don't want you to just go and calculate things without thinking about them. So what I will say though is the following. So I personally don't find this as satisfying as as a way of thinking about the world. But there are plenty of physicists who work this way, and frankly, for most practitioners or users of quantum mechanics, I think most of the time we are on a certain level happy to just apply the results of the theory. Quantum mechanics does make really concrete predictions about the outcomes of measurements and the probabilities one might get of measuring different things. And oftentimes it's, we might just care about, testing those predictions and using those predictions and not really thinking too hard about what's really going on. So I think most physicists are at least some of the time sort of agnostic. There is something about this realist position, right? Because what this suggests is that if a particle has a definite position but we just can't know it, then what this suggests is that quantum mechanics maybe is incomplete. Yeah. So this this whole probabilistic idea of sort of that the world is inherently probabilistic bothered lots of scientists, lots of physicists, including Albert Einstein, who was never comfortable with this idea. So Einstein, in the later part of his life, was investigating things like hidden variable theories. And what a hidden variable theory says is, okay, well, quantum mechanics is sort of by itself inherently incomplete because it doesn't tell you everything there is to know about a particle. So maybe there's some other variable, some hidden variable that's sort of also associated with the particle, and that this hidden variable really contains the information about where the particle really was. It turns out, and this is a story I don't think we quite have time for, although if we decide to do projects, that is something I think would be worth somebody looking into. You can do some experiments to test this sort of idea. So experiments, it turns out the experiments say that non-local, that local hidden variable theories are not consistent with nature. So you can still rescue being a realist if you construct some sort of more involved ways of thinking about how to still have a hidden variable. So this, I'm sort of rubbing a lot of stuff under the rug, but there's sort of the general idea I've sort of outlined here is if you ever want to Google EPR for Einstein-Podolsky-Rosen paradox, and what's also called a Bell's inequality, that will sort of lead you to more information about this kind of thing. I think this is discussed at least briefly in Townsend, and I think you want to see section 5.6. So there's certainly a problem with naive realist theories of interpretations of quantum, but there are still folks who are thinking about how this, whether or not this could be the case, and you might have fun thinking about it for yourself. So there's sort of one more thing I want to just mention before we go, and that's the idea of Schrodinger's cat. So there's a famous paradox in quantum mechanics called Schrodinger's cat. I'm going to cut away to my computer to show you a picture because I cannot draw this very well here. So, Schrodinger's cat is a thought experiment that works in the following way. This was proposed by Erwin Schrodinger, and his idea was, imagine that you put a cat in a sealed box so that the cat's in the box and you can't see inside. Along with the cat, you put in a contraption that contains a small amount of some radioactive substance, such that in, let's say, an hour, there's a 50% probability that one of the atoms inside the radioactive source here is going to decay. Now, if the atom were to decay, imagine that this triggers some sequence of events where a hammer falls and breaks a flask containing poison. Now, until you look inside the box, right, you don't know if the cat is alive or dead. Schrodinger argued that perhaps, this cat is in some superposition state where the cat's wave function psi here is a superposition of being alive and being dead. Now this seems like a rather paradoxical situation, but that's the essence of the cat parrot of Schrodinger's cat. So what Schrodinger thought was that, okay, well, before we go and look inside the box, so the wave function for the cat is somehow in a superposition of alive and dead. And so this raises the question, well, is it looking into the box that sort of forces the cat's wave function to collapse either into alive or dead? And if so, did you really kill the cat by looking in the box, possibly? But on the other hand, right, this seems absurd, right? Because you would think that the cat really was either alive or dead before you opened up the box. Right, and so this kind of suggests that there's something really weird when you try to apply quantum mechanics to macroscopic systems, and that there's something also really funky about wave function collapse. I think that's all I'm going to say about it for now, except to say that if you think this is odd or weird, that's completely natural and probably a good thing. Exploring Schrodinger's cat in more detail might also make a good final project topic if we decide to go in that direction. So the last thing for today, I just want to spend a few minutes talking about where we're going to go going forward. So we've wrapped up our discussion of Chapter 3 of Townsend, and we're going to dive into Chapter 4 on Wednesday. And the theme for Chapter 4 is that it's all about solving the time-independent Schrodinger equation for different potential energies. So we'll start with the finite square well, which arguably is a better model for nature than the somewhat artificial infinite square well we first looked at. We'll also look at a mass on a spring, or something called the harmonic oscillator, which has all sorts of cool applications, thinking about, let's say, like molecular vibrations. We'll also, sort of, as we go through this, think about sort of how to sort of conceptually and qualitatively reason about what solutions to the Schrodinger equation might have to look like, even for cases that we might not be able to solve analytically. That, I think, is really fun. We'll talk a little bit about scattering and tunneling. So if I have, let's say, a barrier, it turns out that in quantum mechanics, particles have some probability of going where they couldn't go classically. We'll talk about that. And then heading towards the end of the course, we will talk about atoms. Atoms are really important for understanding chemistry. If you're an astronomer, for understanding how like spectroscopy works. So we will definitely talk about atoms. We will talk about the Bohr model of the atom, which is sort of the first attempt to apply a quantum-like ideas to atoms. We'll definitely talk about the Bohr atom. If we have time, I might want to at least take some tentative looks at solving the Schrodinger equation for the hydrogen atom. The details of that are really involved, and frankly, the full details will have to wait for 421, but we might sort of start to take a look here. And then, depending on where we are, probably the last topic of the course will be some introduction to nuclei. Again, nuclei are important if you're an astronomer. There's applications for weapons proliferation, for nuclear energy, for sort of the effects of radiation on living things. So there's sort of public health things to be concerned about as well. So lots of rich topics to explore there. So one thing I do want to say, I think at this point we are all through sort of the mathematically and conceptually hardest part of the class. The last week or so, I recognize, had a ton of really hard ideas. You should give yourselves a pat on the back for thinking about some really difficult things. But as we go through the rest of the course, more and more, right, as we look at some of these problems, the only ways to solve them, either involve really, really ugly math or sort of inherently require some kind of numerical approach. So we'll be relying sort of more and more on doing things qualitatively or looking at numerical solutions and just trying to understand what they mean. So if the last week felt really heavy, I think I can say that that the toughest part of the course in some sense is now behind us. And so we'll look at some more applications of quantum mechanics to different potential energies. We'll start to be able to bring in more real world applications and think about things like chemical bonding. So I think we have a lot of fun in the last couple of weeks ahead. And so, as always, please let me know if you have any questions or if there are any things you would like to explore further. And I'll see you next time.